talks. Afterwards, we have a break, and then we again have an open discussion, cumulative, any questions that you have on the program. So, first begin afternoon, Nikos Tziavelis.
Hi everyone, I am Nikos. Whatever I will present here is joint work with my advisors, Mirek and Wolfgang, who are sitting here in the audience. We're from Northeastern University. This talk will be all about ranked enumeration. So what is ranked enumeration? There are many ways to look at it. One perspective is to start from an enumeration problem. And we have seen talks from afar in previous workshops and Antoine about enumeration problems. The idea is that you have a problem that has many, many solutions. Think of a query with a huge join output. Maybe we can't compute all of it at once, but maybe we can compute one answer and then the next answer and then the other one. And in these cases, there's often an order of importance between the answers. So we know what kind of answers we want to see first, and having a ranking function on top of the enumeration gives us this ranked enumeration. Another perspective to look at it is to start from an optimization problem. What essentially I mean, a problem that where we want to compute the best solution to a problem. And there we can ask what's the second best solution, the third best solution, and so on. Both perspectives lead to the same thing, ranked enumeration, so it's a very natural thing. And we also have this more catchy name, like NEK. You can treat it as a synonym. So this talk will be more about when we can do ranked enumeration and less about the how. We started looking at this for conjunctive queries, but we soon realized that the same algorithms and techniques apply to many different problems. And their common link is dynamic programming, and in the spirit of the workshop, semirings. So here's the structure of the talk. First, I will talk about how to start from a dynamic programming problem and immediately get ranked enumeration for it. And then we will apply this to specifically for conjunctive queries. Okay, so first, let's look at how we can see dynamic programming as a DAG. We need some way to describe dynamic programming, like what actually do we mean when we say dynamic programming. And if you open a textbook, you can find a description that looks like this, where we have a DAG. The nodes, you can think of them as the recursive calls, dynamic programming, or you can think of them as the cells in the array that you fill up, and the edges are the dependencies between these problems, and we also have costs to transition from one to the other, and the goal is to minimize the total cost. That's what we do. Now, that's a rather unusual way to think about dynamic programming, so let me show you a quick example of how this works. So this is a very, very simple problem. Find the longest increasing subsequence in a list of numbers. Right, so from 3, 4, 5, 6 is an increasing subsequence. We want to find the longest one. You can do this very easily by going bottom up, dynamic programming, and computing at every state. What's the maximum by looking at all the previous numbers that are greater than that. So it's a very simple thing. And you can ask, okay, where's the DAG here? I don't see any DAG. The DAG are, the edges are basically the dependencies of the problem. Right? And if we materialize them and we also put a source in the target node, we can also see this problem as a shortest path problem. And that's something we can often do for these problems. So in a sense, dynamic programming and the shortest path problem are kind of the same problem.
Not its longest path, right?
Right. So, okay, if you can say that what's the longest path or the shortest by flipping the weights if you treat them as negative numbers. That's why I say this -1 thing. It's the weight of the edges. Okay, so we have this DAG structure. Now, usually when we do dynamic programming, we don't actually materialize this DAG, but we could, right? It doesn't cost us anything, asymptotically at least. So we can materialize this DAG as we do dynamic programming, and this will be important for ranked enumeration. Right. Now let's talk about the generality of this thing. And that's where the semirings that I promised come in. Essentially, the question is, when can we do dynamic programming? And you can look, at the recursive equation that I had before from this example. You can see it has these two operators, max and plus. And You can ask what other kinds of operators can I put in there, and it's not surprise now that the answer is semirings. So I won't go through the definition. We've seen multiple talks today and yesterday. What I want to point out is that this works for dynamic programming, but now if we want to have a ranked enumeration, we need something more than that. And we discussed about this a bit in Kuldeep's talk yesterday. The additional property that we want is selectivity from the plus operator. Essentially, we want the plus operator to act as a comparator. It has to return either the first argument or the second one. And semirings that have this property are sometimes called selective diodes. If we have this property, the natural order of the semiring that we can define actually has a total order on the domain. Here are some examples of semirings. We've seen the semirings yesterday and today. They have appeared all the time. The first three ones, the tropical, the Viterbi, and the Boolean semiring, they all have selectivity, and we can do ranked enumeration for all of them. The question makes sense. For the last one, this natural number semiring, that's a semiring that we use to count things. Right? We can count the number of solutions, count the number of paths. And if you think about it, it doesn't really make sense to ask for a second best solution. And that's because of selectivity. It's the lack of selectivity. Okay, now we have this order now. And what we can show, the proof is very simple. I won't go through it, but essentially we can prove with distributivity that it has a certain kind of monotonicity. If we start with some inequality x less than y, we can multiply on both sides the same thing, and the inequality continues to hold. Okay, and this property is also the same thing as the optimal substructure property in dynamic programming, if you think about it. Essentially what it says is that if you fix an optimal suffix, a subsolution, then you just need to pick the best x or y to find the overall optimal solution. Right? So that's what dynamic programming does. Okay, so with these semirings, the selective diodes, we get a certain kind of monotonicity. But here's where things get interesting, because there are also other kinds of monotonicity. In particular, in work on instance optimal algorithms, there is another kind of monotonicity that I call here holistic monotonicity, just to be able to differentiate. What it says essentially is that if you have an aggregate function and you increase all of its arguments, then the aggregate function can only increase. Now, the monotonicity we are talking about for semiring is actually stronger than that, because we need to be able to do that for any subset of elements. For example, if you pick here 3 and 4, you can replace them with 2 and 8. Think about this in terms of the tropical semiring. Because 3 plus 4 is less than 2 plus 8, we can swap 3 and 4 with 2 and 8, and the inequality continues to hold. This kind of monotonicity, I call it here subset monotonicity for this reason. It has been used in the past for ranked enumeration for conjunctive queries, here in this paper from Benny and Joshua Sagiv in 2006. And it's essentially where dynamic programming lives and where we can do ranked enumeration. Okay, now let's talk about the algorithms. Right. Yes?
What is the ranking function?
Right, so the ranking function, essentially this, you can think of the ranking function as this f. It's you define an aggregate function on the query answers, and you get some scores, right? And then you use the scores to rank the query result. Or if you think about it in terms of semirings, you use the times operator of the semiring to get the scores for each individual query answer, and then the second operator, the plus, which is the comparator, to do the ranking.
But you don't require any other conditional.
No, that's it. I mean, it depends. There is a subtle difference on whether we talk about, semirings or aggregate functions. So for semirings, we need all the properties of the semiring. But for aggregate functions, you can think of this simply like that. You aggregate some numbers, and then you compare your query answers. Is that question? Yes.
So is subset monotonicity always defined? So is the order on the subset always defined as the order on the sum of the elements? So here you say that 2, 8 is greater than or equal to 3, 4 because the sum is greater than or equal to.
Yes. So essentially, you have to use the f here. If this f is the sum, then you're also taking the sum of 3 and 4 to do the substitution here.
So f is like
F is the sum here.
okay, yeah.
And Nikos, I assume your ranking functions don't have fixed arity, right? And this arbitrary number of.
It depends. You can, yeah. So if you think in the world of aggregate functions, you define the function as operating on a multiset, right? That's the usual way to think about aggregate functions. You can take any list of arguments and you collapse them into one thing. But of course, you can also define it on a fixed arity if you want. Right, algorithms. So it shouldn't come as a surprise now that since we can see these problems as a DAG, that in order to do ranked enumeration, we need to find the kth shortest path in the DAG. So essentially, we're talking about algorithms that can do this k shortest path calculation. And this is the best we can do for subset monotone ranking functions. This TTK function here, it means the time that we need to get the kth answer in our enumeration, time to k. And we have to first pay a linear cost. That's the size of the graph or the state space. And then for the kth answer that we get back, we have to pay a logarithmic cost, plus this L is the size of the solution, right? Because we have to write it out. So you can see this is already very good, right? Because the first part is essentially the cost of dynamic programming. And for the second part, we have this logarithmic cost. Now, if you know about enumeration, if you have heard before about enumeration algorithms, you know that usually there's a preprocessing phase and an enumeration phase. And that's essentially what we see here. The first term is the preprocessing, and the second term is the enumeration. You may have also heard about delay for enumeration algorithms. So I think that's a good point to talk also about that. So essentially, what's the difference between the time to k that I just showed you and the delay? So if we are interested in getting the answers as quick as possible, the time to k is the measure that captures that. Delay is more about having regular inter-arrival times. I have here an example on the right. The x-axis is the time, the y-axis is the number of solutions returned, and we have two algorithms, algorithm A and algorithm B. You can see that that algorithm A returns every solution faster than algorithm B, but it has a high delay. So there's this gap here. Algorithm B, on the other hand, is more regular, but it's slower. So there are three things I want to point out here. If we can upper bound the delay, we also get an upper bound for the time to k. So that's good because we can use delay as a sufficient condition to get time to k. Now, if we start from an algorithm that has an already good, whatever good means, time to k, having this additional restriction of a regular delay can slow the algorithm down. And finally, if we talk about lower bounds instead of upper bounds, lower bounds are more general if they're stable for time k. Now, it should be clear that if we talk about a specific problem and we take the best blue algorithm and the best orange algorithm, the blue one will always be on top because it has less restrictions, right? But I think a very interesting question here is whether this gap between that I'm showing here is actually real or not. In other words, are there cases where we observe a large gap between these two properties? And I have two partial answers for that question. The first answer is a paper by Florent Capelli and Jan Stroszewski, where they look exactly at this question, and they show that you can actually translate the time to k into delay for unranked enumeration with a logarithmic cost. The second partial answer that I have is that for the ranked enumeration that I'm talking about here, we actually do have we observe an algorithm that has a good time to k, but its delay is not great. So let's talk about this algorithm. This algorithm, we call it NEK part plus. On the left, we have the guarantee that I showed you before, and you can see what we improve is this logarithmic factor. Instead of log k, we have log n, where n is the number of nodes in the graph. Now, why is this better? For small values of k, these are the same, because the first term, the size of the graph dominates. For large values of k, and k can grow a lot because you can return many, many solutions. For example, it can be n to the power of L, this expression. There we see an improvement. Now, you might think, okay, this is a rather small improvement, right, because it's the logarithmic factor. But I think what's interesting here is that if you run this until the end, and you get all the answers sorted, this is faster than sorting. So it returns the answers faster than a generic comparison-based algorithm. Okay. What I didn't mention is that this new algorithm requires a stronger notion of monotonicity, which I call here strong subset monotonicity. Most of the ranking functions or the semirings that you can think of actually are in this green box. But we also have examples of some that are not, and I have here an example. Let me show you what this monotonicity property is. I have here the definition on the top. But let me show you an example so that you get the gist of it. On the left, we have the tropical semiring. And for this semiring, this has the strong subset monotonicity property. The way to think about this is that we have an observer that is looking at the output of a ranked enumeration algorithm, and it's trying to infer more things about it. For example, let's suppose that we get these three things in the output in this order, like 1, 1, 1, 1, 1, 2, 1, 4, 1. What we want to be able to do is to figure out what will happen if we swap a prefix of the solution, like the ones, with a 2, right? A greater prefix. And for the tropical semiring, it actually works out that if you substitute 1 with 2, you keep this kind of monotonicity. And the algorithm, actually, this is what it does. It keeps track of this information, it stores it, and it reuses that to infer more comparisons as it goes on and on. For the one on the right, this doesn't hold. So what is this? We have minimum and multiplication, and we also have a 0 on the domain, which is an annihilator. So what's happening here is that what can happen is that the algorithm starts returning first 099 and then 011, right? Which, if you multiply these numbers, they're all 0. So it doesn't really matter. And we don't learn anything about what will come after that. So we can't infer from that 199 will be better than 111. So that's the essence of this property, that by looking at complete solutions, we are able to figure out more things. Okay. And finally, I have here a slide with the history of this thing. I mean, as you can imagine, this is a fundamental problem, a k-shortest path problem, and this is my best attempt to summarize what has happened, like all these papers and ideas. There are many details here. What I want you to take away is that there is a line of work that starts from Lawler and Murty. This is a well-known, it's called Lawler-Murty procedure. And this one results in this algorithm that I call here NEK part. And there is a different line of work starting from Bellman and Calaba in the 60s, which results in this NEK rec algorithm. And the new algorithm, this NEK part plus, I mean, that's how the name came about. It essentially combines conceptually ideas from both of them. And that's how we got this improvement for strong subset monotonicity. Okay. So now, how much time do I have left? Like 10 minutes. Okay. So I will talk about how now to take this framework and apply it to conjunctive queries. Here's an example. We have a 3-path query. It joins 3 tables. And we want the query answers to be returned ranked by a sum of weights. And the weights are these columns. So you can imagine that every table has an additional column which describes the importance of a tuple. Right? And we're saying we want the query answers that have the smallest sum of weights first. So what do we do here? We can take this and we can map it to the framework that we just saw, because we can create these white nodes for our tuples. Right? So you can see there are 3 layers of these white nodes, one for each relation, and we can also take our weights and we can put them in the edges of our graph. That's fine. One more ingredient that we need is this form of factorization here. This is only to keep the size of the representation small, because you think of this as a bipartite graph, right? If we do all the possible connections, we can get a quadratic cost. So these intermediate nodes here, y equals 1, y equals 2, only serve to make the representation more compact. And I'll just mention that, this is a natural way to think about many types of, not only equijoins with these equality conditions, but also about other conditions. Essentially, how do you connect these layers? And we have all done this also for inequality joins. Okay, so if you do all that, essentially you get this DAG, right? And the DAG has a source node, it has a target node, and every path that starts from the source node to the target is now a query answer. There's a one-to-one correspondence. So we can just apply what we did before, and we get our ranked enumeration. This works for any query that has this path structure and one relation comes after the other. But in general, conjunctive queries can be more general than that. And we have seen multiple times in different talks in the past about join trees. A join tree is a tree where we can put an atom of the query or a relation in every node, and there's a certain connectedness property. And every acyclic conjunctive query has a join tree. So there's a very natural progression now to think about this problem. I showed you what happens for path queries whose join tree is a path. We can also have tree queries whose join tree is actually a tree. And of course, they can also be cyclic, but that's an orthogonal concern because we can use hypertree decompositions to map them back to queries. So essentially, what's missing here is this middle part, right? We need to take what we did before and generalize it to handle the tree case. And I won't have time to show you how this works, but essentially, there is a notion of dynamic programming that works on trees. I call it here 3DP. It has also been called in the past non-serial dynamic programming. For every algorithm that we have, we need to go through a process of translating it so that it works on the tree case. And we have done that. And the results look like this. Now, this is the results that we get in terms of complexity. I want to highlight 2 things. First, if you think about data complexity, then there's really no difference. We are here, and there's no difference between. There are many algorithms that satisfy this. And this is the same guarantee that I showed you before, this n plus k log k. If we go to combined complexity, and now we also have the size of the query, this is where we observe the difference for this more advanced algorithm. So for combined complexity and strong subset monotonicity, we get this improvement here, which, if you see there's this diam of Q, this is the diameter of the query. So this is what happens when you try to take the results and translate them to the tree case. It gets a bit tricky, but the gist of it is that the more path-like the query is, if it has a high diameter and it looks like a path, the more improvement we get. On the other hand, if it's like a star or very bushy, we don't get much improvement. Also, we have implemented this, and it actually works very well in practice. I'll just show you one experiment here. This is one query. On the x-axis, we have the time, and on the y-axis, the number of answers that the algorithm returns. And if you try to first do the join and then handle the ranking, you won't see any answer for 10 seconds. This is our implementation of this join first strategy, but you can also run it on database systems, PostgreSQL here and commercial system X. Now the order between these two doesn't really matter. Sometimes one is faster, sometimes the other one is faster. The important message is that they always follow this join first approach. On the other hand, our NEK is much faster. It returns the first answer here 500 times faster, and it can also have an advantage even for the last answer because of this faster than sorting. Okay, I don't have a lot of time, but I want to highlight one more thing that I think is interesting here, is that so far I've been talking about the ranking function and its monotonicity properties kind of in isolation. But if we take both the ranking function and the query structure into account, we can potentially get more. There are two aspects that I want to show. One is about lexicographic orders, and Nofar will talk more about lexicographic orders in the next talk. In a lexicographic order, the ranking function says we care first about X, then about Y, and so on. One way to handle it is to map it to a semiring and employ the framework and the machinery we have from before. If you do this, you will get logarithmic delay. But now, it turns out that for certain orders, you can actually get constant delay. And there's a very easy way to see this. For example, for the query we have here, this is the same graph that we constructed before. Observe that if you start from the left and you go to the right, you will always encounter first X, then Y, then Z, then U. Right? So if you just do breadth first search, you get ranked enumeration for this order. And it turns out that if the order somehow agrees with the structure of the query, you get this constant delay. This has been observed in factorized databases. The condition that they use is a bit different, but it's essentially the same as an alpha elimination order. The other aspect that I want to highlight is this notion of a compatibility with a tree decomposition or a join tree. And this is something that from a paper by Paris and Saline Deep. An easy example to understand this is, let's say I give you a function like this, where it's g of xy plus g of yz, where g can be anything, right? Any function. Now, this is not subset monotone because we don't know anything about g, right? But if you look at the join tree of the query, the g functions will resolve locally in each bug, and in between the bugs, there's only a plus, right? So actually, we can do this for this specific join tree, and there is this notion of the ranking function being compatible with a certain join tree or tree decomposition. I have a couple of minutes. Okay, so very quickly, what we just saw is that, ranked enumeration, the same algorithms appear in different settings, and the common link is dynamic programming and semirings. Different monotonicity notions can give us different algorithms, and we could potentially do more if we take the structure of the query into account. We also have what I showed you is very practical. It actually outperforms database systems if you implement this for conjunctive queries. And I have here some questions that are very natural given, I hinted at them multiple times during the talk. We still don't have a precise characterization of tractable queries and ranking functions. So if you think about this outer holistic monotonicity class, we don't have algorithms, but we also don't have lower bounds. So a concrete example is the median as an aggregate function. We don't know what happens there. The other thing that I mentioned is this relationship between time to k and delay. We have some results, but we don't completely understand what's the relationship between them and whether we can always map one to the other. And I think, an interesting question is about circuits. I presented to you here something that I claimed is a general dynamic programming framework. Circuits also claim to have this property. I think it's clear that you can take what I showed you and map it to a circuit. But what's not clear is whether you can carry over all the algorithms. So I think there's some interesting questions to look at there. And that's all. Thank you.
Questions in case there are.
Yeah, so it's really impressive that your implementation is faster than the commercial ones, even when you enumerate the full result.
Right.
So why are they slower? So is it because of a backward plan, or because of are you a really mad hacker or something?
Right. So I think your question is how this gap here, right? This 1.6 times, or even with the other systems. So there's many explanations to this. First of all, it doesn't always happen, right? It happens for some queries. One reason why it happens is that we are reusing comparisons as we are doing the enumeration. And the query answers, they're not independent objects, right? They have a shared structure that you can exploit. And that's essentially what the algorithm does. If you use a generic, a merge sort or quicksort on the query answer, you are treating each answer as an independent object. But you can exploit this, the shared structure, the fact that they all come from the same database and the same input tuples to speed it up. And that's why it happens. But it doesn't happen always. It depends a bit on the structure of the query.
One more question. Maybe Paris, and then let's take the other ones off.
Another more practitioner's question is, so I think it makes a lot of sense that if you do that, you can beat the base instead of if you want to do it like top 10 or top 100. But what do you think would be the right way to push these ideas into a commercial system? So do you redesign a system from scratch and having like enumeration as a first-class citizen? Or is there any way to push these ideas kind of reusing existing machinery that delivery systems have?
Yeah, I think that's the right question going forward. I don't have the complete answer. I mean, of course, I can say, we need to implement this as new physical operators and do everything from scratch. I think it's one of the most important questions right now, how you can map this to what database systems already do and somehow express this as with their primitive operators.
Any thoughts?
No.
Then let's take this for afterwards for the open session. Very interesting to hear, yes. But let's get to that. Okay.